Okay, welcome to our Quantum BW colloquium. My name is Alexander Heinrich. I'm the head of the office of Quantum BW. It's the first time that it's a pleasure to be here to welcome you to our colloquium. And I will guide you to our today's event. For those who are here for the first time, Quantum BW is a state initiative of Baden-Württemberg in quantum technologies. We are pooling the scientific and economic competences to bring quantum technologies into applications. And as an overarching umbrella organization, we try to strengthen the already existing quantum networks here in Baden-Württemberg, to interconnect them and to increase the visibility of Baden-Württemberg as a quantum hotspot on national and international level. And with this colloquium, we want to strengthen and to promote the scientific exchange in our ecosystem and invite every partner from universities, from research institutes, but also those who are already doing research work in quantum technologies in startups or even in companies. So we want to share the newest results in quantum science and also to bring together the ecosystem with this quantum colloquium. Today it's an honor to welcome Professor Jan von Slageren from the University of Stuttgart. Let me introduce you a little bit. You studied chemistry at the University of Utrecht and obtained the PhD from the University of Amsterdam. And at that time he was working on photochemistry and photophysics of transition metal components. Mm-hmm. And after the PhD thesis, he switched the field of his research activities to molecular nanomagnetism, and I think this is where you are doing your research work even today. Then he was a postdoc in Italy with Professor Gatteschi and Cesoli in Florence, and then he became group leader here at the University of Stuttgart with the topic of molecular magnetism. After the habilitation, he went to Nottingham and was a lecturer on inorganic chemistry there. But after 3 years, he came back to Stuttgart as a full professor in physical chemistry, and today you are here. And we are very excited to learn more about your newest results on molecules for quantum technology. The stage is yours.
Thank you very much. So thank you very much for coming here. Thank you very much for the invitation. I'm Joris von Slageren of the Institute of Physical Chemistry, University of Stuttgart. And today I want to tell you a slightly different story. So you will have heard in this colloquium series and in other colloquium series that you will potentially attend stories about how superconducting circuits are going to be fantastic for quantum computing. You will have heard stories about NV centers that are going to sense with close to the quantum limit. You will have heard how all of this is untrue and it's Rydberg atoms that are really going to change the world. Today I want to make the case for yet another platform, which is the molecular platform, and we believe that molecules have great potential to really make some fundamental changes in the field of quantum technologies. Right? So in this venue, I'm not going to give you an enormous introductions of the benefits of potential benefits, one should say, of quantum technologies for society. I think you have heard this all many, many times before. So of course the basic building block of a quantum technology is a quantum bit, any system that has 2 or more well-defined levels and can be put into a coherent superposition state of these levels. And there are many, many different implementations which are currently being pursued. Of course, the fact that there are many of these potential quantum bits means that none of them are perfect. If I want to make a computer chip, I'm going to use silicon. I'm not going to look around for a new material. If I want to make a quantum computer or a quantum sensor, I have to think about which type of quantum bit I use. And that means, of course, that it is not all perfect. So which types of quantum bits are around on the market today? Of course, where the big money is, this is superconducting quantum bits. The big companies, IBM, Google, and so on and so forth, are building quantum computers with now up to 1,000 quantum bits or so. How they are going to get to 1,000,000 quantum bits, which is when it becomes really interesting, of course, is not solved as yet. Longest coherence times, largest numbers of entangled quantum bits, of course, are achieved with ions and traps. And of course, quantum dots have the advantage that they are easily integratable with conventional electronics. Now, there are some platforms where here in Baden-Württemberg and Stuttgart we are very successful in, and this is, for example, nitrogen vacancy centers in diamond. This can be Riebeck atoms, and of course, since already, I would say about 2 decades, the molecular quantum bits. And then, of course, a figure of merit for a quantum bit is essentially how long does it take to make a quantum operation, and what is the coherence time, which is essentially the sum or the time that you have available for the sum of quantum operations. And you see that this figure of merit is, give or take an order of magnitude, essentially the same for all of these. So why consider molecules at all? Of course, there are latecomers to this field, and that means that you have to show some potential advantage. Otherwise, why not use an NV center? Why not use a superconducting circuit? And we believe that the reason is that molecules are almost infinitely tailorable. So that means that I can achieve any sort of energy spectrum that I would like to have. Any sort of anharmonicity is easy to implement. Not always so in other platforms. If I want to couple quantum bits together, I want to switch this coupling, I want to determine the coupling strength, all of this is possible by chemical synthesis. If I have systems with more than 2 states, I can use these ancillary states to implement qubits, so higher dimensional qubits, or I can use this for sort of on-qubit error corrections. There are proposals out there. However, I believe that the real advantage of molecules for quantum technologies is in positionability. And that means that if I want to have few qubit systems, for example, for quantum sensing, I want to, this is my sensing, this is my memory qubit, something like that, or it's a singlet state that I use for sensing, all of these proposals exist. And I want 2 quantum bits, which are 2.3 or 4.7 nanometers apart. I can make this. And competing platforms, this is not always feasible. So the atomically precise positioning in few quantum bits or more quantum bit systems is a definite advantage, in our view, of molecular quantum bits. The second advantage, of course, is that molecules can be self-organized on surfaces to form these almost infinitely large regular arrays, again with atomic precision, and of course in some mixed self-assembly processes you can also tune the distance then between quantum bits, you can also tune interactions between them. So that means that if you want to go from, let's say, 1,000 quantum bits to 1,000,000 quantum bits, this could be an initial step in this direction. And then finally, I believe that one of the advantages is that because these are chemical systems, if I want to sense something chemical, a molecule in my breath, coronavirus, something like that, of course it is easy to implement then a chemical receptor structure in the quantum system to actually specifically bind the analyte that I'm trying to quantum sense. So we believe that these are very, very important advantages. And then, of course, the roadmap, we have some catching up to do in that sense, to demonstrate that molecules are viable building blocks for quantum technologies is the following. We have to demonstrate that the quantum units themselves are competitive. We have to make assemblies of them, so few quantum bit assemblies, but also long-range ordered assemblies. And of course, we have to incorporate these into some sort of device that can eventually be useful. Now, we believe strongly in this, and when I say we, is this initiative here that I want to highlight for a moment, which is proposing to use molecules for quantum architectures, and it's a part of the German Excellence Initiative. So let's go through each of these 3 steps and see a little bit, and I'm going to focus here mostly on the work, of course, that we have contributed to science. Right, so the first question, of course, is, are coherence times competitive? And we believe that they are so. I have given you 3 types of molecules, and the ensemble coherence times are in the dozens to hundreds of microseconds at reasonable temperatures, mostly in this sort of 10 to 100 Kelvin range. And if I look at this graph of the phase memory time as a measure of the coherence time as a function of temperature, you see that all the filled systems are molecules, the open symbols are NV centers, phosphorus and silicon, and so on and so forth. And you can see that on an ensemble level, molecules are perfectly competitive with existing quantum platforms. And the key, because it took a while to investigate this or to find this out, and we sort of demonstrated this about a decade ago, the key is the removal of weakly coupled nuclear spins. And by nuclear spins, these are in chemical systems and molecules very often proton spins. And you can see from these structures that all of these molecules have no hydrogen atoms. Right? This was very, very important. Now, if I take this particular example, which is from our work, this is from Diana Friedman's work, and this is also our work. If I take this particular example and then look a little bit more into the properties, how robust this quantum bit is. For example, I can look at the different frequencies that I could use for addressing these quantum bits, starting at the sort of normal expand of EPR, which is about 10 gigahertz. I could also do this at 3 gigahertz, all the way up to hundreds of gigahertz, and you see that the phase memory time is essentially constant. So these are very, very robust systems. They're chemically robust, fully air and moisture stable. You can also then look at the spin relaxation time, the spin lattice relaxation time, which of course is the ultimate limit of the coherence time. So that is very good. Now, of course, these phase memory times are simple in EPR terms, Hahn-Echo measurements. They are simple ensemble measurements, no fancy tricks. If you start doing fancy tricks, you can of course cool down, or you can start to use dynamic decoupling. You can see that you can easily increase the phase memory time to even higher and higher values. So in that sense, this problem is solved. On an ensemble level, molecular quantum bits are competitive with existing platforms. Now, just to show you that we understand the mechanism of decoherence in these systems, I have brought you a couple of slides. Because these are ensemble measurements, the decay of the signal is essentially due to any sort of process that happens between generating a coherent superposition state here by a 90-degree pulse in pulsed EPR measurements. There is a refocusing of all sorts of inhomogeneities. Then here there is a spin echo. Anything that happens between reading out and creating the superposition state, of course, leads to decrease of the echo signal, which can be an electron spin that changes, it can be a nuclear spin that changes. But it turns out that by far the strongest contributor to decoherence or to loss of phase coherence is these flip-flop processes in the nuclear spin path. And this, of course, we can try to model. So the process looks more or less like this. This is the electron spin, the molecular quantum bit in a coherent superposition state. This is the path of nuclear spins around it. And these nuclear spins will interact among each other. And of course, you can have these energy conserving flip-flop processes, something like this, as far as I get with animations. You can calculate this, and this is a 15-page PRB paper from almost 2 decades ago now. And it assumes that all the interactions are dipolar, and that means that you can, of course, set up a Hamiltonian. This is the dipolar interaction between 2 nuclear spins. And you can use this then to formulate the density matrix. And by only considering these sort of pairwise, of course, you could also consider 3 or 4 partners. This turns out not to be necessary. You can actually calculate the echo intensity as a function of delay time between creating the coherent superposition state and the refocusing pulse. And this is simply the sum of a number of oscillatory terms, where the oscillation frequency essentially depends on this flip-flop rate. By considering all the other interactions, so the interaction of nuclear spins with the electron spins, of course, also dipolar, you can actually come up with a closed expression for the echo decay. So we have tried to use this. This is our quantum bit. Again, this is the crystal structure. I was lying to you before when I said it had no protons, because it has no protons in the molecule, but there is a counter ion, which certainly has some protons. And of course, we know exactly where they are, right? The model was originally derived for phosphorus in silicon. And of course, then the silicon-29 is randomly distributed. On the other hand, we know exactly where the protons are, namely there. And the only thing that I need to do is to sum up over all of these protons, consider all of the pairwise flip-flop processes, and I can calculate the coherence decay. And this is the red line here. The blue points is what we measure. There's no fit in there. So at that point, of course, we stopped making more molecules, because if I can calculate the coherence time, I don't have to make a new molecule and then measure if it's any good or not. Right, so that problem is then solved. I just want to show you that there is a little bit more to molecules than just a spin 1/2 system. We can also use more complicated molecules, such as this one here, which has a large spin in the ground state. So spin equals 5, for example, in this case. And that means, of course, that it is a qubit, right? It has 11 different MS states, and of course, we can, in principle, create coherent superpositions between all of these. Right? And there are theoretical proposals by Daniel Loss that you can use these sorts of molecules to implement Grover's algorithm, and therefore it was interesting at the time to find out if we can actually measure coherence in such systems. And of course we see this Hahn echo, and we see then the phase memory time as a function of temperature. Of course the coherence times are not so long at this moment. But in principle we can actually also make these sorts of qubits with these molecules. A nice factor, of course, also is because these MS states, so the spin orientations, are split up in zero field. By the zero field splitting, this means that the energy gap is already present in zero field. It's 95 gigahertz more or less, and that means that you can do all your quantum operations in principle in zero field. You don't need to apply a field in any sort of direction. Now, that's all very well. These are all ensemble measurements. So my friends that do NV centers, they say, well, it's all rubbish because it's all ensemble measurements. How about single entity measurements? Of course, this is always going to be necessary. Now, microwave quanta have very little energy, so that means that there's not enough energy to detect on a single entity level. And the only two options that you essentially have is to use optical means. So that means to transfer the quantum information onto an optical photon. This is, of course, what happens in NV centers. Or you have to use electrical readout, so that means that the quantum information is transferred to a mobile charge carrier. This is the electrical readout, electrically detected. Magnetic resonance is the technique that goes with that. And of course, this is something that is used in phosphorescent silicon. So where are we in molecular science? This is now not our work, but I want to highlight it here nonetheless. The optical detection, of course, uses this sort of energy level schemes, just like in NV centers. In a sense, you can see these as molecular NV mimics. And there's a number of systems on the market now where this works. Of course, the luminescence contrast and all of these things is not fantastic yet. These are still ensemble measurements, but this is all very, very recent work, so that means that we will get there very, very soon. The alternative, of course, is electrical readout, for example, in such electromigrated junctions by Rubin and Bernstorff is already about a decade old, and here it was possible really to measure a single nuclear spin and perform coherent operation, implement Grover's algorithm on a single quantum bit. So in principle this problem has been solved, but not in a way that it is really general, let's say. Right, so we have quantum units, which I think are quite reasonable. So now let's see, can we make assemblies of these? Small assemblies, few quantum bits, or larger assemblies. This is the second step in our roadmap. And one of the first steps, of course, is to make few quantum bit systems. And this we can do. I can put one here, I can put one there, and of course I can very, very well control the distance and the coupling between those. And the system we have chosen to work on is these radicals. You can see there are no hydrogen atoms, and they are completely stable. You can store them for decades, they will not break down. You can easily functionalize them, so you can put in a chemical group to couple them together, to couple them, immobilize them on surfaces, couple them to other systems, NV centers, also all possible, right? And of course, one of the first steps that you can do is then make a system with two centers. There's one radical center here, one radical center here, and then see if you can do a basic 2-qubit gate operation. Now, first of all, the coherence times are really fantastic in this CS2 solution. So again, ensemble measurements, they are about 100 microseconds, so it's not bad at all. This is sort of the ranking of best molecular quantum bits ever. You can see that they are really up there with the best of them. But what is really interesting, of course, is then if I can use this for a 2-qubit operation. And of course, for example, the C0 gate consists of a 2-qubit part and a single qubit rotations, where if you break down the sequence, and this is of course already from the times of NMR quantum computing, you see that there is this part where there is an evolution of the first quantum bit under the influence of the second quantum bit. And that is what we are going to determine here. In EPR terms, this is double electron-electron resonance measurements. This is the pulse sequence here, so I make a coherent superposition state here. I manipulate the other quantum bit and see then what the influence is on the first quantum bit. And this is this blue line here, and the oscillations here are essentially directly a measure of the interaction strength between the two quantum bits. I can assume a dipolar interaction, then I can convert, of course, this oscillation frequency to a distance, and you can see that the distance is 2.3 nanometers and not 2.4 or 2.5, but it's very, very well defined. So that works, even though these are very narrow line systems, so it's not so easy to address two qubits separately, but it turned out to be possible. Now, of course, in many quantum processors, you are not going to be interested in 2 qubits or 3 qubits. You want to have many of them. And then if you have such a generalized quantum technological device, you will have some molecular qubits that you want to perhaps immobilize on the surface, and potentially you want to read these out by an electrical current, right? So and that means that this is essentially a first step going from assemblies to devices. So let's see if we can actually deposit molecular qubits on surfaces while retaining their properties. Maybe they break down, you don't know. So this is the first step I want to spend a couple of slides on. And this is a work that was published last year, where we deposit molecular qubits. Is work by a master student then and my postdoc Lorenzo Tesi. And what we are going to look at in this part of the talk is simply the deposition of molecular qubits and then demonstrating their functionality after immobilization. Now, there are different approaches to immobilizing quantum bits. Of course, you can try to have these highly organized and highly regular arrays, which in chemistry terms are, for example, metal-organic frameworks. If each of these colored parts here is a quantum bit, you see that you have a number of quantum bits which have very, very well-defined sub-nanometer precision distances, and therefore very, very well-defined interactions between them. You can do this also in 2 dimensions on surfaces. This has been also demonstrated in literature, but perhaps not for all applications it is necessary to really have these highly ordered arrays. If I want to have a quantum sensor, I can also use small ensembles of quantum bits on surfaces. And this is the approach that we have taken in our work, which is using self-assembled monolayers which have a high degree of ordering, maybe not atomic precision, on surfaces. Now the point is, if I immobilize a molecule on a metal surface, very often what will happen is that the molecule will keel over. The spin-bearing part will interact with the surface, charge will be transferred from or to the surface, and the coherence properties are lost. So this is what state of the art in the literature before we started. And what we have done, which was, I think, a very clever idea, is to have this modular approach, where first we make a self-assembled monolayer on the surface, and this self-assembled monolayer can be functionalized in a second step with a functional unit, in this case, the quantum bit. So, in chemistry terms, we have taken a surface, we have immobilized this azido and decaying thiol, which has this group, which is reactive. It can react with the other end of a potential molecular quantum bit, in this case, a stable radical called tempo. And this is a nice type of chemistry, which is called click chemistry, won the Nobel Prize, and we can make these sorts of units here. At that point, of course, we have a highly organized array of immobilized quantum bits. Now we can go through the analytics. We can see, well, this is my azido group here before immobilization. This is after immobilization. It has worked. We can do the X-ray photoelectron spectroscopy, show the same thing. We can do the near-edge extended X-ray absorption scattering, and we can show by these ways that first of all, the process is complete. Quantum bits have been immobilized, and we can also show that there is not large amounts of Fizeau species. We can do cyclic voltammetry to immobilizing on an electrode to really demonstrate that we have one monolayer coverage. Right? So we have this highly organized system, and then of course we are interested in the coherence properties. And it turns out, and this is the first time that this was measured, in situ on a monolayer of these quantum bits, it turns out that the coherence properties are maintained. So this is the field-swept echo-detected EPR spectrum. This is the building block itself. This is the monolayer. And you will see that even if you don't understand the details of the spectrum, they are essentially the same. And that means that this is the echo-detected spectrum. Of course, the echo sequence creates a coherent superposition state in its first step. So that means that the fact that I see a spin echo means that coherence is somehow preserved in the monolayer. Now, of course, then we can measure by changing the delay between the pulses, we can measure the decay of coherence at different temperatures. And then what we find out is that the coherence time as a function of temperature is rather constant. This is the self-assembled monolayer, is the red symbols. The blue symbols are the building block itself. And you see that in a two-dimensional surroundings, actually the coherence times improve, potentially because the nuclear spin path is only two-dimensional in nature, something we are investigating at the moment. So that works. Now let's see if we can actually go to devices in this way. So I have shown that we have these assemblies on surfaces. Of course, the next steps there are to investigate the interactions between the quantum bits. These are rather dense systems, and then of course the next step would be, for example, to see if we can do single entity addressing, for example, by ESR combined with STM and so on and so forth. But these are still, in a sense, assemblies. Of course, then I could do the same thing. I could immobilize the quantum bits on a device structure, and then to see if I can, for example, integrate this with conventional electronics. And that means that we will look at quantum devices here. This is the same picture again. Now we have shown that we can, in principle, immobilize quantum bits on a surface. Now the question is, I don't want to then spend the rest of my life doing EPR measurements on ensemble level to address these quantum bits. I want to see if I can read out through an electrical current, for example. Optical means would, of course, be an alternative. Now, first step is then to see if I can do this at all without looking at these, which is already more challenging, at these immobilized species on surfaces, but to look at the interaction between mobile charge carriers and molecular quantum bits. This is something that is already slightly older. In the meantime, many people have worked on this topic, and I will just very briefly then present the results here. Now, of course, we want to do something like that. We want to have quantum bits, we want to have charge carriers, but we are not so sure how strong the interaction between the charge carrier and the quantum bit should be. Because if the interaction between the charge carrier and the quantum bit is too strong, then the electrical noise generated by the charge carrier is going to destroy quantum coherence. One of the reasons why ESR STM, so looking at molecules in an STM setup, always leads to coherence times of hundreds of nanoseconds, rather than the dozens of microseconds that it can be. On the other hand, of course, if this interaction is too weak, then the charge carrier will never see the quantum bit. So we have to somehow find the optimum there. And because we don't know this in advance, we have thought to just make a very simple approach where we mix the two components together. So we have a semiconductor, which provides the charge carriers, and we have a molecular quantum bit. And then by having a mixture of these, of course, there will be quantum bits which are closer and which are further away from the charge carriers. And we hope that in this distribution, at some point, the relevant interaction strength is also present. Now, just a bit of chemistry. We have looked at this particular polymer, which is called PHD. It's a well-known semiconducting polymer, also much used in organic photovoltaics, organic light-emitting diodes, these sorts of things, which is then combined with an electron acceptor, which takes away one electron from the semiconductor, of course, and generating charge carriers. These are polarions because they are combined with lattice distortions and so on and so forth. So this is a well-known system, and we add to this this particular molecular quantum bit that we know very, very well and has coherence times up to 40 microseconds in spite of having some proton spins. Now, of course, this looks very clean. In reality, probably the system looks a little bit more like that, with very crystalline parts. Of the violet parts are the semiconductor, and of course the red spins are the polaron spins, and then the quantum bit is also in there. Right? And of course there are some of these more amorphous parts where the interactions will be different. Now, first of all, of course, I need to figure out if by putting paramagnetic species inside my semiconductor, I'm not destroying the conducting properties. So we have looked at conductivity in this is essentially organic field effect transistor measurements, because later on we are going to look at zero gate voltage to look at the quantum properties. We have added this acceptor to generate the charge carriers and looked at this at various different temperatures. Now it's a very interesting field, the field of organic semiconductors or conducting polymers, because there are 100,000 million papers at room temperature and there may be 10 at low temperatures. So there's certainly not so much known about these systems at low temperatures. Typically because you don't want to run your solar cells at 10 Kelvin or so. Right, so we have done this. This is P3HD with the quantum bit. Incorporated is drop cast, so you just drop it on your transistor substrate. And if I don't add this electron acceptor, of course, there's no measurable current. Here is a bit of thermal activation. But if I add the electron acceptor, I have the polaronic charge carriers, and you see this is an important number. From about 15 to 20 Kelvin, you see that the charge carriers start to become mobile. You can also analyze this in terms of variable range hopping, something that at this point I will not go into in detail. Then, of course, the question is, okay, I have these polaronic charge carriers, I have my quantum bit inside, does coherence survive in this case? And it does. So let me talk you through this figure. If I add no dopants, so that means there are no polaronic charge carriers, I see this field-swept, echo-detected spectrum, which is very typical for copper, believe it or not, as you wish. And that means, of course, I can generate coherent superposition states. If I add the dopant, I see the same signal plus an additional signal, which we attribute to either the electron acceptor or the polaronic charge carrier, or potentially a combination of both. That is not so important. What is important, of course, that I still see the echo signal due to the quantum bit. So that means that even though there are charge carriers present, the quantum coherence survives. So this is a very important piece of information. Now, those of you that pay attention are going to say, well, this is at 7 Kelvin, right? At 7 Kelvin, these charge carriers are not mobile. And of course, this is a very valid observation. And that means that, of course, we have to look at the temperature dependence. So in red, we have the conductivity again that I showed you before. About 15 Kelvin, the charge carriers start to become mobile. And in blue, I have the coherence times, which are, of course, not perfect in this highly protonated system. They are about 2 microseconds, and then you see when the charge carriers start to become mobile at 15 to 20 Kelvin, you see a drop in coherence time, but you still have coherence times of about a microsecond. And a typical quantum bit manipulation times of 10 or 20 nanoseconds, this is actually still quite a lot. Right? So that means that we have demonstrated that quantum coherence survives even in the presence of mobile charge carriers. Why did I not measure the higher temperatures? That's simply because there are not so many spins in there, and at some point the Boltzmann is against us and the signal is simply too big to measure. Good. Now how do we proceed from there? And we have not managed to do the final story yet. Of course, we proceed from there by not doing the standard electron paramagnetic resonance measurements, by looking at the electrically detected magnetic resonance measurement. So essentially, you are measuring the current, you are doing the transport measurement under the influence of microwave radiation while changing the magnetic field. And then if I do this, if I have my microwave radiation present, I'm sweeping the field. Of course, at some point, the EPR resonance condition is fulfilled. I start to flip the spins of the charge carriers, and this leads to a measurable signal. The mechanism is usually something like that. The transport process is usually some form of hopping process, and of course, an electron or a charge carrier can only hop to a trap state if the spin of the electron that is already present in the charge in this trap state has the opposite sign, right? And by influencing these statistics with microwaves, I end up with a measurable signal. And this actually works, is well known. This is on the P3HC, so on the polymer itself. And of course, then the next step is to irradiate at a frequency or a field where I'm flipping the spin of the quantum bit rather than of the polar link charge carrier, and then see if this leads to a measurable signal in the electrically detected magnetic resonance spectrum. We are not there yet, but we are making good progress, and we hope to achieve this soon. Now, I think I have time for a final little topic, which is a little bit more into quantum physics, which is to show an advantage of molecular quantum bits that I have not stressed in the beginning, namely that their density is very, very high compared to, let's say, a defect density in a semiconductor and so on and so forth. And the idea is, of course, if I put lots of spins in a resonator, or in general of a cavity, and the spin excitation frequency and the cavity resonance frequency are the same, then of course a coupling between the two systems can occur, and at that point the states have mixed nature. And this is then, of course, you can see from these sorts of anti-crossings in the field frequency versus field plot. You see that in this central part, of course, the coupling between the cavity states and the spin states occurs. Now, the idea is to use these sorts of mixed systems to store quantum states. So I can input microwave pulses into this ensemble. I can store them for a certain time, and then by using a strong microwave pulse, I can actually retrieve these pulses and they will be emitted again. Right? This is quantum repeaters or quantum memories are the sort of application scenarios that are proposed there. And the bottom line will be, and I will show this in the end, is that molecules have a much, much higher density than anything else out there. Now, just a couple of formulas. Of course, for the single spin, the Hamiltonian is the capital Hamiltonian, so these are essentially the number states of the photons. There is the spin Hamiltonian, which in the simplest case is just the same on Hamiltonian. And of course, there is a Hamiltonian that describes the interaction, which is this one here. And this leads, of course, to these sorts of polaritonic eigenstates. Now, the point is that the coupling between spin and photons is very, very weak. And this is in a millihertz regime, of course, at that point, is not really, how can I say, viable for any sort of application. You can try to improve the single spin photon interaction by limiting the mode volume of the resonator or by increasing the frequency, and people have achieved, I don't know, about maybe kilohertz or something like that, right? But it's never going to be megahertz or something like that. So, fortunately, if I consider a spin ensemble, then the effective coupling between the resonator and the spin system goes as the square root of the number of spins. And this is where the advantage of molecules comes in, because even in a very small sample, we have many, many, many spins. Okay, we can look at the cooperativity, so that is this coupling between the cavity and the spin system divided by the loss rate of the cavity, kappa, and of course the decoherence in the spin system, which is gamma. And if this factor is larger than 1, you talk about strong coupling, and we'll see in our case this can be much, much higher. Okay, we can then, of course, from this formula, calculate the cavity reflection. We can fit our curves or the measurements that we do. And these are the measurements that we do. We have looked at another stable organic system. This is what we call PDPA. It has this name. And the cavity that we use is this so-called Fabry-Perot resonator. It consists of one flat mirror and a curved mirror. And you can see that if with a vector network analyzer, I look at the reflection from the cavity as a function of frequency and field, I see this very clear anti-crossing. And that means that the effective coupling from the gap size is 80 megahertz. Now, of course, this is much larger than the loss rate of the cavity and is much larger than the decoherence of the spin system, so that means that we are in the strong coupling regime. You can see is probably too much light here. There is this very faint line in the middle. These are not impurities. This is simply because there is an inhomogeneous broadening in the spin system, which we can model as a sum of discrete spin ensembles. And if I do this, this is reproduced by the simulation, which is shown here. Now, of course, we can start to play games. We can, for example, do this sort of Hahn echo measurement. And we are exciting here in the middle of this empty crossing. So you can, of course, say, well, why do I excite anything at all? Because if I do the Fourier transform of this pulse, the frequency content is certainly not enough to excite these polariton modes. But it turns out, of course, that the edges of these pulses, these are square pulses, contain a much higher frequency range, and it is actually the edges of these pulses which are exciting the cavity spin system. So that is at 35 gigahertz, and this is then the spin echo that we measure. Now this is a homodiode system, so this should be essentially just an echo. Instead, we see this very, very strong modulation. And it turns out that the modulation frequency is exactly the distance between the excitation frequency and the frequency of the polariton mode. We can prove this by tuning the microwave frequency, and you can very clearly see once you arrive at the polariton mode, this modulation is gone. And if you go in between the two polariton modes, it increases, and at some point you can even see the two modulations. By this very strong pulse, right? This is 3 orders of magnitude stronger in power, and what we then measure is these echoes. And you can prove by changing the sign of the phase and so on and so forth that that the echoes come out, of course, in inverted order as you would expect. You can also try to determine the efficiency, and that means that for every photon that goes in, about 10 to the minus 5 photons come out, so it's not very efficient. But I think in terms of temperature and efficiency is certainly competitive. This I can show here, and this is where the real advantage of molecules comes. This is because BDPA has this very, very high spin density. So if I look at numbers of spins per cubic millimeter, in phosphorus and silicon I have about 10 to the 14. At the highest doping levels in NV centers I have about 10 to the 15. And in molecules, I have orders of magnitude higher, right? So here's 10 to the 18 in our BDPA, which is 3 or 4 orders of magnitude higher. And that means that if I want to use the numbers of spins that I've been using, the sample that we use was just a small 5 millimeter pellet. If you want to do the same in NV centers or phosphorus and silicon, you have this enormous big block. Now, looking at the efficiency, this is the efficiency of storing microwave pulses as a function of temperature. Of course, these lumped element resonators, this is Hannes Meyer and these people, you see this very, very high efficiency, up to 1% or 0.1%, but of course the temperatures are very, 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 very low. Whereas in our case, we could go all the way up to room temperature. Of course, the efficiency is about 10 to the minus 5, so in that sense, much bigger. But in that sense, it's competitive, certainly also with existing systems out there. Okay, I think this is all I have time for. I have tried to give you an overview of where we are with molecules in quantum technologies. I believe there is much work left to do. I hope that the reviewers will be nice to us and they will grant us the money for the excellence cluster, and we will do many, many important things. I focus here mostly on my work. Of course, there are many other people, especially also in Baden-Württemberg, that do very work, let's say, at the cutting edge of the field. The work that I've been talking about was done by these PhD students, starting with Christoph about 15 years ago, so we have been working in this field for a while. Many of the samples come from people elsewhere, polymers. The XPS measurements are semiconductor engineering friends, and I want to acknowledge all of them. It's impossible to be able to do everything yourself, as you very well know. Finance has come from these foundations, so the IQST, very important in Baden-Württemberg, the Carl Zeiss Foundation and the Baden-Württemberg Foundation have also funded this. I'm very grateful to them. I'm very grateful to you for coming here and paying attention to this talk. Thank you very much.
Thank you very much for your talk and these really exciting insights in what's possible with these molecular spin qubits. And yeah, we are now ask you for your questions. Are there first questions to our speaker today?
Maybe I missed it, but how does the two-qubit gate, how do you address a single qubit and how do you couple two different qubits and make a two-qubit gate?
Yeah, I did not spend too much time on, of course, how do I address. Most of what I've shown to you here is essentially electron paramagnetic resonance, right? So these are microwave pulses, because the splittings in these systems are, of course, in the microwave regime. I'm applying magnetic field, right? So this microwave pulses, I create a coherent superposition state. I can do a refocusing of inhomogeneities in the ensemble, and I can measure spin echo. Of course, there are many other things that I can do. One of the things that I showed was the double electron-electron resonance, where I manipulate one spin and then the second spin, and I see what the effect on the coherence in the first spin is. The coupling of between qubits is usually mostly dipolar, right? So these are always uncouplings, and simply the two qubits are 2 nanometers apart, which turns out to be some so and so many hertz as a coupling strength. There are now also first works on switching this coupling by, for example, including a photoactive spacer in between, which I can excite, and it goes from a singlet, so diamagnetic, to a triplet state, and at that point, of course, through the exchange interaction, you get an interaction between these two qubits. This is a Nature paper from last year where they have shown this. So there is also some potential to actually switch the interaction between the components, using then visible light essentially to switch this coupling. Okay.
Maybe directly continuing to this question. So you showed the operation for the C0, where the J appeared. So J was the dipole-dipole coupling strength. And this is what you control by the distance, I guess. We have the spacing in between. So you have very well controlled J due to your molecular structure.
And these are rigid systems, so there's also no temporal variation, right? It does not oscillate or it does not fluctuate.
And in those molecular systems, how is the coupling mapped then, actually? So you have dipole-dipole, yes, but what can you realize? So in terms of coupling?
In principle, you can realize what you want. Right? In long rings ordered arrays, you can make these square arrays, you can make triangular arrays. There's enormous amounts of literature on the sort of topologies. Nobody's ever looked at the quantum properties of these. It's usually about either other types of applications or simply about creating new topologies. There's enormous flexibilities, and this is then controlled by the symmetry of the building blocks. Right? If the building block has some 120-degree angle, then you are going to build a hexagonal or something. If it is 90 degrees, it's going to be a square or something. And of course, then by using more building blocks, you can make more intricate and more complicated structures.
Also in the third dimension?
Yeah, so.
And when you talk about energy levels that these two qubits have, like, are those molecular energy levels which are in the ground state?
Yeah. So far what I've shown is all ground state. So these are paramagnetic molecules. They typically have a single ampere electron, and then by applying a magnetic field through the Zeeman splitting, I generate the energy splitting that I want. You can also go to higher spins. There are also, of course, also molecules with spin 1, spin 3.5, spin 2, and so on, whatever you want. And then, of course, you have a zero field splitting, which already creates an energy splitting in zero field, which then starts to play out again in these centers, for example. And the nice thing is, of course, I can make the splitting as big or as small as I want. If I want to have a splitting of 1 gigahertz, fine. If I want to have a splitting of 100 gigahertz, is also fine. That's the nice thing about molecules, in my view.
Do we have any questions from the chat?
No.
Not yet, okay. Are there other questions here on site?
Maybe one very important question. So you talked a lot about the coherence times. What about the number of 2-qubit gates you can realize in the decoherence times?
That is an open question as yet. Right? We are doing first steps in making these 2-qubit gates. To have shown you something very basic in this double electron resonance measurement. Of course, we have not done in the same measurement than the single qubit rotation. So exactly, there is this one paper on implementing the Prof algorithm where they went a little bit beyond that. So this is not my work, so I don't have the numbers in my head. How many gate operations they could do before the.
Is there a rough estimate about the gate times in general?
Well, in this case, of course, the gate time, this is evolution. And then it depends, of course. Right, you see that this is in somehow in the microsecond, so this will be in megahertz, more or less. And then if your coherence time is some dozens of microseconds, you can sort of figure out, right, this is 1 or 2 orders of magnitude. So let's say 10 to 100 ballpark figure. Of course, the idea is that if the qubits are too close together and the interaction strength is too strong, then it's no longer possible to do single qubit rotations. Right? Because the interaction is always on, so that means that your 10 nanoseconds or whatever you need to do a single qubit rotation, if this is no longer very fast compared to the interaction strength, then you are in trouble.
Okay. Maybe we start with you.
What are the fundamental limits or lower bounds on this technology? Like, where are the most errors come from, and how do you think you can tackle those?
Well, these are spin-based qubits, so whatever is valid for other spin-based qubits, I would say is also valid for molecules. Right? So this is very well known where the limits are. I think it's also very well known how to deal with such errors in terms of error correction. I think there is no fundamental difference whether you use an NV center or a molecule. I think the fundamental difference is that, of course, an NV center has the advantage of being very, very stable. It's very easy to read them out on a single entity level, which in our case, of course, has been done, but not on a, how can I say, is still quite challenging. On the other hand, of course, molecules have the advantage of being easily positionable. So there is this trade-off, and it depends on how far we can get if this platform is going to be competitive with these sorts of things. Yeah, so the errors are the same, right? So there's decoherence effects, which we know very well. There is, of course, imperfection in the pulses, right? So that means that you don't have exactly the right superposition that you're trying to generate. I think these are well known.
So another question?
Yeah, I mean, especially how do you account for the crosstalks? Because the in the gigahertz range or megahertz range, where the energy differences between these qubit system will always be there for other levels also, right? Like when you put a magnetic field, they also get split, right? In a molecular system. How do you only
well, in terms of other levels, this is not necessarily an issue, right? There are these 2 spin levels or others, whatever, how many you have. I think this is not what is going to be the issue, I suppose, is if you have a dense system. Of course, I don't have the more than just the interaction between qubits, but I will have some neighboring qubits. They also have dipolar interactions. Of course, most of what I've shown you is in dilute systems, so then this sort of crosstalk does not occur. The leakage, let's say, between states on the same qubit, I would say these are T1 processes, right? So unless, of course, your splitting is small compared to the excitation bandwidth, these sorts of things. But this is not normally the case. Because then the excitation bandwidth is somehow dozens of, not even, maybe a megahertz or so, and the energy splitting is easily gigahertz, so you're not really exciting other states.
Once again, no question online? Okay. Then maybe a very last short question, maybe it's a stupid question. You showed your slide with the memory, and you just said in one sentence, because of cavity effects, the coherence time is even at room temperature very high.
Yeah.
Have you also an idea to use some cavity effects that are not resonant to all the other processes for the computing platform, to use them to fix them? Because I understood that the temperature where they start to move is very, very relevant for the coherence time. Is there any idea to stabilize that in a non-coherent way to other processes, maybe?
Oof, I would have to think about that. That sounds like a very interesting idea.
Yeah, because it changes, from your slides, I saw that it changes extremely the situation. And maybe you can combine it.
Yes. Well, in essence, of course, we are automatically moving this direction then by incorporating the transport with the coherence measurements. And then if we have enough spins, we are going to run into some coupling effects anyway. So I will tell you in a year or so.
Yeah, I would be happy to hear about this idea in a year, what comes out. Thank you very much again for your talk, for answering our questions. Thank you all for being here, and thank my colleagues from Fraunhofer IAF who had invented the Quantum BW colloquium and are organizing all the events. Thank you very much, and it's a pleasure to invite you to the next Quantum BW colloquium, and it's on 7th of November, and we are looking forward to Professor Markus Müller from RWTH Aachen presenting his work with a talk on the dawn of quantum fault tolerance. So, see you again on 7th of November and have a good afternoon. Thank you very much.